Welcome back, everyone. I hope you had a good first week of remote learning. We are leaving electricity and magnetism and we're starting a new unit all about waves. We're actually going to have 4 lessons on waves, so you'll do it both this week as well as next week. So a wave is something we're really familiar with. Ocean waves, earthquake waves, light waves, sound waves, microwaves. You've heard all these words before. So it's just a disturbance of moving energy from one place to another. The best way to think about this is to think about sports fans doing the wave in a stadium. So I've got a picture there to kind of get it in your head. So the wave's coming, it gets to you, you stand up, you put your arms in the air, woo! And then you sit back down. You, the matter, was temporarily displaced. You kind of moved, but you didn't move across the stadium. The energy of the wave moved across the stadium, but the matter was just temporarily displaced. It was temporarily put out of its normal position. Now, there are 2 major types of waves. There's mechanical waves and electromagnetic. Mechanical waves have to travel through matter. So they have to travel through a solid or a liquid or a gas in order to move. If they don't have matter present, they will not move. And a great way to remember this is that mechanical and matter both start with the letter M. Electromagnetic waves, on the other hand, and a good example of this would be light waves, can travel through matter. So right now, in whatever room you're in, you probably have a light on somewhere. That light is an electromagnetic wave that is currently traveling through the air. So it's traveling through matter. But light doesn't have to travel through matter. It can also travel through a vacuum, like outer space. So the sun's light, for instance, goes from the sun to Earth, traveling through a vacuum. So it doesn't need matter there in order to get from one place to another. So that's the major difference between those two, whether you have to have matter or whether you don't. So there are 2 major types of waves, electromagnetic and mechanical. There's also 2 major shapes of waves, transverse and longitudinal. Now the pictures that I have at the bottom of the screen are both of the first type, transverse waves. And for most of us, when we hear the word wave, this is kind of what comes to mind, this shape, where it goes up and down and up and down. So with this, the movement of the matter is in a right angle to the movement of the wave. So look at the ocean wave there. The water is moving up and down and up and down, but you see the arrow that says that the wave is moving from left to right. So the energy of the wave is moving sideways where the matter is moving vertically. So you have that in right angles or perpendicular to each other. The other type, longitudinal waves, the matter and the energy of the wave move in pretty much the same direction. So if you look at this picture, it kind of looks like a slinky. If you gather the slinky together and kind of squish it together and then let go, it'll kind of pulsate through the slinky. In fact, when I normally am in a classroom showing this, I normally pull out a slinky and show you that movement in person. But our major example for this is going to be sound waves. In fact, that's going to be our only example of a longitudinal wave in this unit. So before we move on, I just want to make sure we're good with all those new definitions. So all waves are either mechanical or electromagnetic. And the big difference there is whether they need matter or don't. Then we have the 2 different shapes. So mechanical waves can be either transverse in shape, where the energy and the matter are perpendicular, or they can be longitudinal in shape, where the energy and the matter go in the same direction. But if you're talking about an electromagnetic wave, which is what we'll cover next week, they are all going to be transverse in shape. You cannot have a longitudinal electromagnetic wave. All right, so now let's talk about the parts of those 2 different types of waves. So the first one we're going to do is the longitudinal wave. Now, these words look complicated, but they're already based on things that you know. So the first word is compression. Well, if you think about compressing something or pressing it, you think about squishing it. That is exactly what's happening in that picture. So you can see that the matter has been squished together for the compressions. Rarefaction, on the other hand, starts with the word rare. So if something's rare, you don't find it very often. It's uncommon. So that's what's happening in the picture there, where you can see that the matter is stretched apart. It's rarely there. So what happens with a longitudinal wave is there's a part that's compressed and then a part that's stretched out, and then a part that's compressed and a part that's stretched out. Now let's talk about the parts of a transverse wave. And these might be familiar to you. I know I cover some of them in earth science when I'm talking to students about ocean waves. So it's possible that you know these words. If you don't, I'm going to go through them. So the top part of the wave is called the crest. The bottom part of the wave is called the trough. You can see both of those labeled on the picture there. And the equilibrium is basically where was the matter before that wave came through. So it's the resting point, the halfway point between the crest and the trough. Now, how tall your wave is called your amplitude. So you would start at your equilibrium and measure up to your crest, or start at the equilibrium and measure down to your trough. Amplitude is important because it tells us how energetic the wave is. So if we think back to that stadium of sports fans doing the wave, you can think about that really gung-ho fan that the wave comes and they're excited and it comes and they stand up and their arms are way up high and they're like, woo! And then you have that person who's on their phone, they're like, whatever, the wave's coming, they maybe kind of toss a hand up in the air and that's it. The person who stood up way up high, way higher amplitude, way more energy in comparison to that person who couldn't get off their phone long enough to participate. So they put in a little bit of effort and had a little bit of amplitude to their wave. And then the last part of the wave we need to talk about is the wave length. And it is just the distance from one part of a wave to the same part of the neighboring wave. So don't get overwhelmed with all the different options there. It's just same to same. So if I was talking about a transverse wave, it would be from crest to crest or from trough to trough. It doesn't matter as long as I choose two identical parts. For a longitudinal wave, I could choose a compression to a compression or a rarefaction to a rarefaction. Again, it doesn't matter what I measure as long as I measure from one part to the next same part. How often we have those waves is called frequency. So a way to look at this is by looking at the frequency that you make to, say, a grocery store. So how often are you visiting a grocery store? So the number of wavelengths that pass in a certain period of time, your number of visits to a grocery store in a certain period of time. So if you go to the grocery store every 2 or 3 days, maybe that's a high frequency wave. It's like, here's a visit, here's a visit, here's a visit, here's a visit. In comparison to if you're going and buying a whole bunch of groceries and going very rarely, maybe you're going every week or every 2 weeks, then here's a visit. Here's a visit. Here's a visit. So low frequency is not happening nearly as often as the high frequency wave. And if we look at these pictures, you can kind of start to notice some things. So wavelength and frequency are inversely related to each other. And we had those terms at the beginning of the semester. When one goes up, the other one goes down. So in this top picture, how would you describe the wavelength? I described it as small. So what would you say for the frequency? Would you say high or low? I said this was high frequency. So you can see small wavelength has a very high frequency. I like to think about it with the length of time. If I'm going to the grocery store all the time, I have a high frequency, and the length between each visits is really small. in comparison to the bottom picture that has a really large wavelength and a very low frequency. I'm going not very often to the grocery store, and when I do go, there's a long distance of time between each visit. So inversely related. When one goes up, the other one goes down. The last thing that I need to cover, and this will be more important for the next lesson, is wave speed or wave velocity. And that very, very directly means how fast is the wave traveling. One thing that you may have heard of before is the speed of light. That is a speed that light always has if it's traveling in a set type of matter. So the speed of light in air, the speed of light in water, the speed of light in space. That is it for us today. Make sure that you do the assignments and let me know if you have any questions.